The Center for Research in Advanced Materials, Monterey Unit, in collaboration with UANL. Removal of total arsenic from aqueous solutions using nZVI geoheterostructures. Arsenic is one of the contaminants present in nature. It occupies the 20th place in abundance, and its mobility extends to acidic or basic conditions. The intake of this metal could cause gastrointestinal disorders, cardiovascular disorders, nervous system damage, and, inevitably, death. The primary sources of arsenic contamination are industrial and mining effluents. They also occur due to natural causes such as diffusion in groundwater and thermal water sources. In countries worldwide, and the most critical case is Bangladesh, millions of people are at risk of drinking water with arsenic pollution. Recently, applying individual absorbent materials such as nanoscale zero-valent iron nZVI and graphene oxide geonanoparticles have shown improvements in removing a series of contaminants in aqueous solutions with less absorbent material. On their own, nZVI and GEO must be removed in later steps once the contaminant have been adsorbed. For that reason, the remotion by immobilized nanoparticles on a micrometric lateral size material such as GEO could be the response to an easy recovery. This work presents the development of heterostructures based on nZVI nanoparticles and GEO. The nZVI geosynthesis was carried out in a reactor using reducing agents such as sodium borohydride. Figures show the diffraction pattern of the nanoparticles without GEO, in which the characteristic peaks of iron oxide are observed, as well as the peak of nZVI. The presence of this iron oxide is normal due to the high reactivity of nZVI. Figure B shows the diffractogram of the samples containing GEO, in addition to the presence of nZVI. The yellow arrows indicate the areas where the GEO sheet can be seen. The dark points correspond to the dispersed and anchored nZVI nanoparticles. In the micrographs, the increase in the concentration of the precursor solution of iron nitrate can saturate the surface of the GEO sheet. This saturation effect can lead to loss of nanoparticle dispersion and the formation of agglomerates that reduce the active surface area. The graph shows the behavior of the nZVI GEO at different concentrations of precursor solution and a comparison with its non-combined species of nZVI and GEO. The GEO does not show arsenic retention, while the nZVI shows a retention percentage of 20% after 180 minutes of the test. The best concentration was 0.015 mol per liter, with 90% arsenic retention after 180 minutes. The highest retention occurs during the first 20 minutes. Later, the retention rate decreases. For low concentrations of arsenic, the presence of the contaminant was not detected by ICP. The nanoparticles dispersion at 0.015 mol per liter concentration provides a greater active area.
Finally, the nZVI geoheterostructures showed significant advantages over their independent species, allowing us to find that in the nZVI geo ratio of 0.5 presents the highest retention percentages of arsenic in aqueous solutions, reaching retention percentages higher than 90% for concentrations of 20 to 120 milligrams per liter of arsenic.